It is a great pleasure to welcome everybody to this WACQT virtual workshop on quantum technology. My name is Giulia Ferrini, and I'm one of the PIs in the Wallenberg Center for Quantum Technology. And the goal of the workshop is to gather young, brilliant scientists and hear from their results on quantum technology, along with a few keynote speakers that will also introduce the topic of the different sessions with their talks. So Anton, you have a slide with the program for today. So we have 2 days ahead. We started today with 2 sessions on quantum computing and quantum simulation. And then tomorrow we will have a session on quantum communication and quantum sensing. So yeah, without further ado, I would like to give the floor to Anton, who will give an introduction to the Wallenberg Center of Quantum Technology, when you can hear about our activities. So please, Anton.
Thank you, Giulia. And welcome again, everyone following online or watching this recording later. So I will just give a brief overview of WACQT, the Wallenberg Center for Quantum Technology, which is organizing this workshop. Here is the one slide with WACQT facts. So we are a center in Sweden, which was started in 2018 with 2 main goals. The first being to build a broad competence base in Sweden for all areas of quantum technology, so computation, simulation, sensing, and communication. And the second main goal, to build a quantum computer based on superconducting circuits. So to do this, we have 2 parts. We have a core project, which is to build this quantum computer. And we have an excellence program, including all these areas of quantum technology, which will be the topics in this workshop. The center is directed from Chalmers University of Technology in Gothenburg, where currently I and Giulia are sitting in our offices. And we also have nodes at other Swedish universities in Lund and in Stockholm, for example. So this center, as I said, started in 2018, and it's funded for long term, for 12 years until the end of this decade, with a funding of in total about 1.5 billion Swedish kronor. If you divide by 10, you get it in dollars or euros. So about 150 million euros. And the funding comes mainly from the Knut and Alice Weidelenberg Foundation, which is a private Swedish foundation, which funds a lot of research in Sweden. We also have a number of industry partners in this center, so it's a quite close collaboration with industry. I will mention a few more things about this. And we are part, for example, of some European programs, also like the Open SuperQ project to build a European superconducting quantum computer, and the Euro QCI for quantum communication in Europe. You can find our homepage here, waqt.se, or our Twitter account, waqt_Sweden. Briefly, this center is organized with, well, we have a scientific advisor board led by Steve Gervin from Yale, board led by Helena Gustafsson. The center is directed by Per Delsing, and we do research in, as I said, in all these areas of quantum technology. We also have a large graduate school and a large guest researcher program. Feel free to contact us if you would like to come and visit. And as I mentioned, industry collaboration. So our industry partners are a number of mainly big Swedish companies like Ericsson, AstraZeneca, Saab, Volvo. But then we also have a number of smaller companies or other partners that help us with enabling technology for the project. With these big companies, we explore how quantum technology can be applied in different industries. So we have industrial PhD students with all these companies. And speaking of companies, in the last year or so, there has been quite a few spin-outs from the center. So we are now really turning quantum technology from science into applications. So there are spin-outs here in quantum sensing, quantum computing, different components for quantum computing, quantum communication, and we have a big holding company for taking care of IP from the center. Let me just mention a few things about the core project we have. So to build a quantum computer. So this is really a full stack approach, the full quantum computing stack being done at Chalmers. And we are doing this both with discrete variables and continuous variable setups with superconducting circuits. And we are now basically scaling up after having demonstrated that we have good control of the basic building blocks. So we have currently a 25 qubit device, and the aim in the plans for the center is to have a 100 qubit device after 10 years, which is not that far away, 10 years after the start of the center. We are now in our 6th year. And let me just finish with showing you a few recent highlights. So from the past year or so from the center, in all areas of quantum technology, we have a lot of work that we are proud of. We have come up with and implemented fast 3 qubit gates that are both more powerful and faster than current 2 qubit gates used in superconducting circuits. We have in continuous variables created several interesting states, for example, a cubic phase state. We proposed new scheme for quantum error correction. We have improved methods for quantum process tomography, which I think you will hear about a bit later today in the talk. We have in quantum sensing developed ways to really slow down light and use that for different applications in metrology and medicine. And on the quantum communication side, we recently developed and demonstrated a very efficient source of photon pairs. So with that brief overview, I just want to say, we have the Wallenberg Center for Quantum Technology here, positioning Sweden in the second quantum revolution. And we have about 130 people at the moment in the center, but we have open positions at several levels, which you are free to check out and find on our webpage. With that, I think I might be a bit early even to end this. So if we look at the program, we have now in the first session our first keynote speaker coming up, Kristel Michielsen. And then we will have a number of students, postdocs from groups around the world. And a second keynote after our lunch or dinner break, depending on where you are, Stefan Philipp, and then a number more talks here. So do we have Kristel already?
But maybe Anton, just for fairness.
Or maybe first, yes, do people have questions about this?
Exactly. So one thing I wanted to, maybe we can take the occasion to see if people have questions on the center, if they have curiosities, or on life in Sweden, you know, like people who might have an interest to come and visit us. So if anyone has questions, or like on our scientific results as well, please feel very free to ask. And thank you, Anton, for the nice introduction to the center.
Yes, you can either raise a hand on Zoom or write in the chat if you have questions, right? everything was very clear.
Else, maybe we should wait 5 minutes before starting again, because I think that there might be people who could tune in for Kristel's talk. So
Yes.
it feels unfair to anticipate the start of her talk.
Yes, I see Kristel is in the among the participants. We could switch. I could stop sharing my screen, and we could check that everything is working on your side, Kristel.
Okay, Anton, let me try, because I just had my computer shutting down completely. So let me see whether everything.
We have quite some time.
Yeah, we have a lot of time. We are ahead of time. Perfect. Okay.
But you see also my screen, yes?
Yeah, now we see it. We actually see it in the presentation.
Yeah, I can change this. So now you see it.
Yes, now we see it. Kristel, I suggest that we wait maybe 5 minutes so that people who might have wanted to tune in for your talk will actually have the possibility of listening from the beginning. So I will temporarily stop the recording. Okay, it's a great pleasure to introduce Kristel Michielsen, who will give a talk on simulating quantum computers. So please, Kristel, the floor is yours.
Yeah, thank you very much, Julia. And first of all, thank you very much to you, and thank you very much to Anton for the invitation. So I will talk about the simulation of quantum systems, mainly quantum computers, but I will have a quite generic talk. So why do we want to simulate quantum computers? First of all, because we want to validate the design of the physical realization of some quantum processors. And as we know, there is quite some variety of quantum processors. But another thing we also want to do is we want to investigate the performance of quantum algorithms that are carried out even on ideal quantum computers, so simulated on a conventional machine or on a physically realizable quantum computer. So actually simulation is a tool which is essential also for cross-platform benchmarking. So the first and most simple quantum computer to simulate is what we call a paper and pen, or a pen and paper version. It's the one that one finds in textbooks, and you're all familiar with this. So if we have a quantum computer or a spin 1/2 system with 1 qubit, then this is how we can describe the state of this quantum system. So we have 2 basis states denoted by the 0 and the 1 state, and we have 2 complex coefficients which fulfill this condition here. Now this can be simply extended to an n qubit system. So, and then we see that actually this state of our quantum system can be represented by a vector that has length 2 to the power n, and that contains all these complex amplitudes here. So that's for the hardware of this pen and paper quantum computer. The quantum algorithm is a sequence of quantum gates, which are the elementary operations that can be carried out. And they are described by unitary, and these are most often sparse matrices, and they change the state of the quantum computer. So actually, if we operate such a pen and paper quantum computer, what we do is we multiply the wave function with a unitary matrix, and this several times. Now, it's believed that we can do this and that nature knows how to do this operation in one step if we have a quantum computer. So, but as I mentioned, this is a belief. We don't have any empirical evidence for this. But if we follow our belief, then the quantum computer is really a good parallel computer that can multiply a 2 to the power n by 2 to the power n matrix and our 2 to the power n vector in one step. Now, everybody who's simulating on a conventional computer knows that this is not possible. So we see here that in theory, we have an exponential speedup. So we have now one step, one operation, instead of 2 to the power 2n operations if we normally carry out this multiplication. Now, this exponential speedup, we have 4 algorithms that can exploit the parallelism. And unfortunately, we do not have many of these. Actually, the Shor's number factoring algorithm is basically the only one who can use this exponential speedup. In practice, we always have to measure the outcome of the quantum computer because it's nice that the quantum computer does some calculation, but we also want to know what it has been doing, and therefore we have to measure. And I will demonstrate you that this measurement can actually kill your exponential speedup. So if we look in theory and we have our pen and paper quantum computer, then it gives as an output a new state psi prime if we operate with a unitary operator on its original state psi. So then we have 2 to the power n complex amplitudes, and we know them all. So from this, we can calculate the probabilities. So also all probabilities are known. If we go to a real gate-based quantum computer, then the situation is different. In order to know what the outcome is, we have to perform measurements, and each measurement will, for every qubit, give as a readout a value 0 or 1. So each measurement gives us one of these 2 to the power n basis states. So from this, it's clear that we will need many measurements in order to get these frequencies here. And the question is then, how many times do we have to measure? So you can already see that if each of these amplitudes, each of these complex amplitudes would be different from 0, then we have to measure 2 to the power n times. And we also want to have some statistical accuracy. So this means we also have to repeat our measurements for a number of samples. So you see here the exponential number of measurements that one would have to carry out if each of the amplitudes would be non-zero. Now, the nice thing about the Shor algorithm is that only a small fraction of these amplitudes is different from 0, and that's actually why this is working for the Shor algorithm, but not for others. For example, doing some calculations with superconductivity would be extremely difficult because the wave function for superconductivity would turn out with almost all of these amplitude being non-zero. So if we want now to do a different type of calculation, so study the full dynamics of a closed quantum spin 1/2 system, which is a model for a gate-based quantum computer, but also for a quantum annealer, then we do something different. So in that case, we have to solve the time-dependent Schrödinger equation. because the dynamics of our quantum system, which is the quantum computer, will be modeled according to this time-dependent Schrödinger equation. So here we have two ingredients. We have our wave function psi, which now depends on the time. And this is again this linear combination of all possible qubit states, which is 2 to the power n for an n qubit quantum computer. And psi always completely describes the state of the quantum computer at the time t. And then we have here our Hamiltonian, and this Hamiltonian models the quantum computer and the annealer hardware, but not only that, also how the qubits in the quantum computer are controlled. So here you see a model for a universal quantum computer. So you recognize here a single qubit term, and here you have a 2 qubit term, and such a term is required in order for the qubits to communicate with each other. So in order to be able to carry out computation, there is no computation without communication. So, and then we have here some time-dependent parameters, which are here the exchange interaction, and here a time-dependent magnetic field. And our spin 1/2 particles are described in terms of the Pauli matrices. Now, for the gate-based quantum computer, the quantum algorithm is this sequence of elementary operations that change the state of the quantum processor according to the time-dependent Schrödinger equation. And actually, it's nothing else than a product of unitary transformations that operates on the states of the quantum computer. Now, if we carry out one of such qubit operations, then what we have to specify is the time interval tau during which this operation is active. And of course, we also have to give the values for J and H, which appear in our Hamiltonian. But here we assume that they are not time dependent, so that they are fixed during the operation of the pulse. So, and then in general, what a quantum algorithm does is nothing else. It starts from an input state of the quantum computer. Then we carry out here one or more of these operations, and the quantum computer will end up in a different state, which gives us the output. So this is for a closed quantum system. We can also study the full dynamics of an open quantum system, or in other words, a quantum computer that is connected to an environment. And how do we model this? Then our Hamiltonian contains 3 parts. So one is the Hamiltonian for the quantum computer, hardware in its control. Then here we have a Hamiltonian which describes the heat bath, which is another spin 1/2 quantum system. And then here we have the interaction between our quantum computer and the heat bath, which models the environment. So with this, we can study temperature effects of the environment on the quantum computer, but we can also model all kinds of errors, and not just the depolarizing channel, which inserts X, Y, or Z gates with specified probabilities to mimic some gate errors, but we also have all types of other errors that can be induced due to the interaction between the quantum computer and the environment. Of course, if we study such an environment, then we assume that in the environment we have more spins than in the quantum computer. And on our systems, our computer systems, the total amounts of spin 1/2 particles or qubits is 43. So this means that the number of bad and spin systems is smaller or equal than 43. So now, how to solve the time-dependent Schrödinger equation numerically? Let us start from a very simple system, namely one single particle which moves in an electric field. So the mass of the particle is denoted by m, and v is the potential energy. So actually, this is the time-dependent Schrödinger equation where phi is now the wave function, and this is our Hamiltonian, the energy function. Yeah, the solution contains all dynamical information on the system, and we know from this differential equation that we can write the formal solution in this way. So we have a time evolution operator which operates on an initial wave function. Now, that's nice that we have this formal solution, but in general, we cannot write the explicit expression for the solution in a closed form. So this means that in general, we have to rely on numerical techniques to solve this initial value problem. So let us see how we can do this in one dimension. If one wants to solve such a differential equation on the computer, the first step we do is we discretize. So, and we discretize in the following way. So X is discretized in terms of J delta, where J is an integer and delta is just a lattice spacing. And here the second order derivative is approximated by this expression here. So, and then we get a form for the equation that is suitable for simulation. So with the discretization, we can write the time-dependent Schrödinger equation in this form. So here we have our wave function written down as a vector. And here we have a matrix expressing our Hamiltonian. So recall that all elements here are complex numbers, and that for V, we have this discrete form here. So actually what we did is we have transformed our partial differential equation, which was continuous, in this type of matrix equation. And we have some hidden problem here. So if our matrix H, which represents the Hamiltonian, cannot be brought in diagonal form analytically or by brute force numerical diagonalization, then it's impossible to calculate this form here. So brute force numerical diagonalization we can always do, but if the system becomes too large, then this does not make sense or simply becomes impossible. So this means we have to come up with something else. So, and what we then do is we propose an approximation for this time evolution operator. And we do this for a well-chosen time step. And then we integrate the time-dependent Schrödinger equation by a repeated application of this approximate time step operator. So we do it in this way. So we have here the exponent divided by m, and then of course we again have here the exponent m. Now in quantum mechanics we have some extra constraints, namely the total probability in our simulation should always be conserved. we can never, like in this case, we are talking about the dynamics of a single particle. So it would not be reasonable that during our simulation, the algorithm is such that it can create or remove part of the particle. That's impossible. So in order to avoid this, the approximate time evolution operator should be a unitary operator. And this is the characteristic of a unitary operator. So the inverse should be equal to U dagger. And here it's a crucial observation that if we now change our wave function by any unitary transformation, that the total probability does not change. And there is a very simple proof for this. So you can, I would say you can easily prove this yourself. I will not spend time on this. And other things or other characteristics are that if this time step operator or the approximate time step operator is unitary, then this implies that we have a numerical method that is unconditionally stable. And the reason is that the norm of U is equal to 1, whereas the necessary and sufficient condition for stability is that the norm of U is smaller or equal than 1. Another nice property of this type of algorithm is that one can easily calculate the local error. So the error from, or the maximum error, which one makes in a single step. And that one can also easily determine the maximum global error after n time steps. So one has here some tools or some handles to control the errors that are made. But the nice thing, it's always stable. So what is then the simulation strategy? So the simulation strategy is a Trotter-Suzuki product formula approach. And in quantum computing, one often sees the terminology Trotterization. And I want to point out here, this is nothing new. This is something which is existing for quite some time. So Trotter was writing about this in 1959. Then Suzuki came up with it in 76, 77, making all kinds of approximations, second order approximation, fourth order approximation, and so on. And using it numerically for solving the time-dependent Schrödinger equation was described already in 87. So every time you now see it appearing in a quantum computing, I would say, article, please remind that this is a well-established method which is known for quite some time. So what is a simulation strategy? So one has to look for a composition, a decomposition of the Hamiltonian in terms such that the exponential of the matrices are unitary. And why? That's because any product of unitary matrices is unitary itself. And again, this is a very easy proof to make. So, but you only have to remind this for now. And actually, this is something easy. So if we take for the terms Hermitian matrices, which have this property here, then the exponential of the Hermitian matrix e to the power IA is a unitary matrix. So the only thing is we have to, if we decompose our Hamiltonian matrix into other matrices, then we have to search for matrices that are Hermitian, and then everything is fine. So for the simple example of the single particle in an electric field, what we do is we decompose our Hamiltonian in 3 terms, 1 for the potential energy and 2 for the kinetic energy. And in this case, we assume that L is an odd number. So for the potential, that's very easy. We have here a matrix with only elements on the diagonal. For later on, this is very convenient because it's very easy to calculate the exponential of a diagonal matrix because it's again a diagonal matrix. And then we have here the 2 kinetic energy terms. And what we here have are matrices that are block diagonal, and they also have the property that they are that it's then easy to calculate the exponential of such a matrix. From our experience, and not only our experience, it is known that the second order product formula algorithm is usually sufficient for simulation purposes. And that's how it looks like. So in the middle, in this case, we have the exponential of the potential energy term. And here we have the kinetic energy terms that are involved. As I already mentioned, this matrix here is diagonal, and the elements are the exponential of the diagonal elements of the matrix V. So that's very simple to calculate. And here we have to deal with block diagonal matrices, and these are simple 2x2 matrices. So we have to calculate the exponential of this one here, and you see this is easy. How do we come to this? So we have these 2 factors here, and we have to calculate the exponential of the IAX, where X is a matrix with elements 0, 0 on the diagonal, and here 2 times 1. And then we simply have these coefficients. Now, in order to calculate the exponential, we make use of this series expansion. And then we have to see what all these terms are. So x to the power 0 is simply the identity matrix. X to the power 1 is X itself. And then, as you can see, it repeats. So from this, one can write the expression for the exponential of the matrix X. And from this series expansion, ordering it in 2 terms, one with coefficients of the identity matrix and one with the coefficients for the matrix X, one recognizes that this is the series for a cosine function and that this is a series for the sine function. So you see, it's very easy calculation. So with these expressions, one can see how one has to calculate the exponential of the matrix with K1 involved and with K2 involved. So we have actually the cosine on the diagonal, except for one element. Here it's the bottom element here, and here it's this left top element. And for the rest, we have zeros or the sine function involved, and all other elements in these matrices are 0. So to calculate this is an order L method, which is really efficient. Now, in case of a quantum computer, we have seen that this is the general expression for the quantum computer. And then what we do is we have to solve the time-dependent Schrödinger equation with this formal solution. And if we then have to compute the operation of our time evolution operator on an arbitrary state phi of the quantum computer, we do it in the same way as I have been describing for this single particle in the electric field. So we introduce a time step tau, so that we have our approximate time evolution operator. And then we take here also the product formula approximation, and we take the second order approximation. So in the middle, we have the X component of the Hamiltonian, and left and right, we then have the Y and Z components. So we can then write the exponential of the alpha component, where alpha is X, Y, Z, as this product. And then one can recognize that what one has here is a product of single qubit gate operations, and the second one here is a product of 2 qubit gate operations. So that's how one can map this whole thing on the trotterization known in the quantum computer articles. If time allows me, and I hope so, that I still have some time.
Yes, Kristel, you have 7 minutes more or less, so that we can keep 3-4 minutes for questions.
Okay, so I have another 7 minutes, you say? Yeah.
Let me see. Yeah, because I would say so. Yes, exactly.
Okay,
So
very good. Yeah, okay, very good. Thank you very much.
You're welcome.
So what can one do with all these simulations? So let me give a brief overview of our history. I will not explain everything here. So, but in 2000, we started with a nice tool which everybody could use under Windows on a laptop. And this was a tool where one could simulate or model the hardware of the quantum computer, and then in these windows make a quantum algorithm. So here you see, you bring the quantum computer in an initial state, and then we carry out the algorithm, which is just a repetition of C nodes. And the initial state was a 1-1 state. Then one could repeat this for a singlet state, and again perform these measurements. Now, this was a pen and paper quantum computer, so this carries out exactly what we expect from a textbook. Then we could say, okay, we now model a different type of quantum computer, namely an NMR quantum computer. And then one can see if one is carrying out the same algorithm, so 5 C nodes on the initial state 1-1, that there is a slight deviation from the ideal quantum computer, but we can still say this is all fine. However, if one does it on a singlet state, then here one sees this does not correspond at all to what we expect from an ideal quantum computer. So here, as I said in the beginning, it's nice for studying the design of real hardware. One can also build other types of hardware, model other type of hardware, and see how the quantum computer behaves on a simple algorithm. Then from 2007, 2017, we have been working on a massively parallel simulator of the quantum computer. And here you can see that we at that time could simulate about 45 qubits on the biggest system. So this was at that time the K computer in Japan and the Sunway Tahuilite in China. In this case, we have a representation of the quantum state with 16 bytes, and then we could maximally simulate these 45 qubits. Adding 1 qubit would mean that we would have or would need a computer that would be twice as big. So that was simply impossible. Then in 2018, 2019, we made an approximation in which we did not represent the quantum states with the 16 bytes, but only with 2. And actually then we could simulate 3 extra qubits. So we could go to 48. Now, and I will not explain the details here, now we have a simulator that runs on GPUs, on GPU clusters. And actually, this is not only good to simulate quantum computers, but also to benchmark conventional computers. Why? Because these simulations of a quantum computer on such a cluster are very memory intensive. So for 40 qubits, we need 16 terabytes of memory. It's also network intensive. So if we have global gates, then we need to transfer 1/2 of all memory. So this means if we have 40 qubits, we have an 8 terabyte transfer of data. We use a huge amount of GPUs. So I would say it's good to test clusters. On the other hand, it's also useful for studying hybrid algorithms, and actually together with our colleagues in Sweden and Julia, we have been solving the simplified tail assignment problem with the quantum approximate optimization algorithm exactly with this code. So here, the GPUs on a conventional system played the role of a quantum processor unit. And this code is very efficient. So the compute time is constant, and the MPI time is linear, so much less than exponential in case of weak scaling. And as I mentioned, we have been doing these simulations starting on laptops, then all types of conventional computers, now on our GPU cluster. And when we install the first European exascale machine in Jülich, then we will also use it not only to benchmark our exascale machine, but we will also use it to run or to benchmark hybrid quantum classical algorithms on a larger scale. So with this conclusion, I would like to stop my presentation. Thank you very much.
Thank you very much, Kristel, for the very nice talk. I applaud on behalf of the audience. We have a few minutes for questions. Do you have any question? You can unmute yourself or write in the chat. Any of the two would work. Well, while people think about questions, I would like to ask you, Kristel, can you go back to the slide where you had a comparison of the different supercomputers simulating? There were two, but the most recent one, let's say, yeah, this one. So here yeah, so here the Jureco and the Jewels, they are both Ulip-based computers, right?
Yes.
That were, okay, that however, okay, that stopped and now, or are you still, are they still in use?
So we have here three Jülich computers. UQueen was an IBM Blue Gene machine. So that was an IBM Blue Gene Cube. And Eureka and Jewels are systems we still have, although Eureka is now a different machine. And Jewels, we still have the Jewels cluster here, which is in this case, because this is a CPU simulator. So that's the CPU part of the cluster. You can see that the scaling on these clusters are not so good as on UQueen and the Sunday Tachylite machine, but that simply has to do with their architecture. So the cluster computers are not so efficient as the machines we have here on the left-hand side. But nevertheless, the scaling is still good.
Very nice, thank you. So we have another question by Shanawat. Yeah, of course, go ahead, Shanawat.
So one thing that I never understood about using GPUs to solve the Schrodinger equation is that inherently, if you try to solve this, you are trying to solve ODE, even with the Trotter-Suzuki. So inherently, it is a sequential operation, unless you can find block diagonal structures that you can break down the matrix multiplications and kind of parallelize it with thousands of cores in GPU. But inherently, you have to it's a sequential algorithm, like you take the first step, then the second step. So I'm curious, is there some smart things that is done and finding this block diagonal structure? Because if I just think about, as you showed, the memory part, the brute force way to do it would just never fit in the GPU. So yeah, my question is how is the GPU helping here? Because you have to anyways do this sequential matrix multiplication with large matrices. You cannot parallelize it.
No, it's parallelized. The code is massively parallel, and this is not different for the GPUs as it is for the CPUs. So the question is here, and I have it here. How does the simulator manage all these complex numbers? So because what you have to do is distribute the quantum states over the multiple compute nodes. That's the question. And for this, we have indeed a technical, let's say, trick, so to speak. So if you look into the case for 40 qubits, then we have 16 terabytes on complex numbers. And for this simulation methods, memory is the limit here, because we don't make any simplifications in terms of the circuits. What our goal is to simulate general circuits. So we don't take into account that one can break them into pieces and things like that. So we simulate everything in full. And if we have 16 terabytes on complex numbers, we have 64 gigabytes per node for 256 nodes. So if we have here our 256 compute nodes, then we have here our 256 MPIs with rank 0 from 255. And then we have what we define as global qubits and local qubits. So for the local qubits, we do not need any communication. For the global qubits, we need communication. And that's what I have been talking about before, that in order to do this communication, we have to do an exchange of data, which is up to half of the data that has to be exchanged. And the only reason now is if we do this with GPUs, that then we have here 4 GPUs per node. So we can, in that case, do more global qubits. So, but the MPI communication scheme is exactly the same as we used for the CPU. We only make use of the fact that we have 4 GPUs on one node.
Thank you very much.
But if you like, I can give you some references to this. Just write me an email.
I will write an email. Thank you very much.
Okay, thank you so much, Kristel. Again, yeah. So in the interest of time, we should proceed with the next speaker. So I would like to ask to Aziza to please share the screen. So now we are going to listen to Aziza Almanakly, who is going to talk about emitting and absorbing a directional microwave photon with waveguide quantum electrodynamics. And I will maybe signal you when it's a few minutes before the end of the time. You can go ahead, Aziza. Thank you.
Hi, how are you doing? Can you see my screen?
Yeah, we see the presentation mode, which is fine, but if you feel more comfortable, you can try to switch to, only your slides visible for us. Else it is not a problem, I imagine, to also see what will come next.
Hello?
Yeah.
Sorry, I don't know why my Zoom just crashed. You can see?
It's on progress. So we see your presentation mode. So we
Okay.
also see the slides that will come.
Okay.
That's okay for us. If you have the option to switch to the, like a full screen mode, and then we will not see your future slides. It's up to you.
Yeah. Do you see the future screen? Or...
Yeah.
Or sorry, you see the full screen now, right?
No, we still see also the presenter mode. But I guess that's okay. I think if it's not bothering you too much, we could maybe start anyway. Aziza? Maybe we can just go ahead with your slides as they are, with the presentation as it is, like.
Yeah, I guess it's causing it.
Let's do that. Let's do that.
Crash. Okay. Okay. It says it's loading. You see?
Yeah, perfect.
Okay.
Just go
All
ahead.
right.
Yeah.
All right. Hi, everybody. My name is Aziza, graduate student at the MIT Engineering Quantum Systems Lab. And today I'm going to talk to you about a project that we've been working on within the Waveguide Quantum Electrodynamics team, which is all about emitting and absorptional microwave photons.
You can maybe just click on the next slide.
Yeah, I guess it's not about the presentation. It's I think something about the Zoom is. Can you hear me?
Yeah, we can hear you.
Okay. Let me try one more time. I'm so sorry.
It's we understand it's not your fault.
Yeah. Okay. Are we good?
Yeah, this looks smoother. Thank you. Yeah.
All right. Okay. Okay, anyway, this is the project, and the motivation behind this project is to use. Do you see these bubbles? I'm so sorry. This is. How long have we been using Zoom, and it's still an issue?
Yeah.
We can see the main slide, but if you change.
I wonder if you would like maybe I could suggest, like in case it would be possible for maybe switch the speakers, and I have now Alec in case it will be tuned. And in the meantime, you can, Aziza, send me your slides, and then we can, coordinate that. I can share the screen. And okay, but now we see your second slide. Can you scroll down now so that we know if they will work? They don't seem to be working. Or
do you see the animations?
No, they don't work now. So can you please, if is the Alec here, maybe we could switch the two speakers. Alec? Okay, now we see something happening here.
I guess there's a lag.
There is a lag, but what happens if you continue to scroll? Just I wanted to make sure that we will, that it will not happen at each slide. Can you convert in PDF? Aziza, can you please convert to PDF?
I think she's frozen again.
Yeah. So I see that Alec is here in the
Yeah, hi. I'm here. I'm happy to go ahead if that would be best.
I would ask to Aziza to convert the presentation in PDF, and in the meantime start with you, Alec, so that we will have a 10 minutes delay. So Aziza, can you hear me?
Yes, I can.
So I
so sorry.
Following that, you please convert the presentation in PDF and also send me the presentation in case of emergency. And we take now, in the meantime, Alec, and then we switch the two talks then, and we will have 10 minutes delay. Okay, so is that okay, Aziza?
Yes, of course. I'm so sorry.
No
I don't know
problem.
what's happening.
No problem.
Thank you.
Please, Alec, would you like to share your screen?
Yeah, let's see if I can have better luck here.
I also had some Zoom unexplained problem a few weeks ago, so I understand that can happen.
Okay, can you see my screen?
We see your screen, yes.
Okay. Great. So
sorry, I didn't introduce you. Okay, we then have Alec Eickbusch, who is going to talk about the realization of an error-corrected quantum memory beyond the break-even. Thank you, Alec.
Great. Yeah, thank you. It's great to be here today. I'm a graduate student in Michel Deveray's group at Yale. And today I'll be talking about our experiments over the past 4 years or so, ultimately towards realizing this experiment that we just published in Nature on realizing quantum error-corrected memory with logical coherence beyond break-even. And so it's a bit of a shorter talk today, so I'll try to sort of just cover the most important points from this research, but I'd like to overview the topics from 3 important papers that led to this realization. The first being our 2020 experiment, which was the first realization of quantum error correction of grid states of an oscillator. And next, our 2022 experiment, where we took these tools and extended them to realize fast universal control of a harmonic oscillator. And finally, how all of this came together and we sort of optimized the experiment in order to realize this metric of quantum error correction of logical memory with a coherence that is about 2 times longer than any of the physical qubits in the underlying system. And if there's time, I'll mention that we're currently working on doing logical gates on these error-corrected codes. And I'd like to mention all of the great collaborators that have worked on this research. There are more than I can even fit in one slide, but this has been sort of a massive collaboration amongst the experimental groups of Michel Devereux and Robert Scholkoff at Yale, and also the theory support of Shruti Puri and Steve Gervin and Liang Zhang's group. And the primary contributors to this work are Philippe Campaigna-Barr, who's now at INRIA Paris, Stephen Tuzard, who's now at National University of Singapore, and Vlad Sivak, who is now a research scientist at Google. Okay, so to begin, for those who might be unfamiliar with the idea of bosonic error correction, what we are doing is taking the state of a logical qubit and encoding that redundantly within the many levels of a harmonic oscillator. And we like to call this a hardware efficient approach to quantum error correction because it gives us these many quantum states that we can use in order to encode information and detect and correct quantum errors on that information without needing many, many physical systems. And so there are sort of number of different ways to do this encoding. And one way to visualize the various types of quantum error correcting codes of the oscillator is to plot their phase space representations. And so what I'm plotting for you here is the Wigner function, which is the quantum quasi-probability distribution, where the x-axis is the position and the y-axis is the momentum, for three of the sort of most popular bosonic quantum error correcting codes, the CAT code, the binomial code, and the GKP code. So this is the phase space representation of the maximally mixed state of the code. And so there's been a lot of theory work looking at sort of what is the optimal encoding considering different types of error channels of the oscillator. And this work in particular looked at numerically optimizing these codes for photon loss error here on the x-axis and dephasing error on the y-axis. And in particular, this GKP code has been shown in this work and in some other works to be optimal for correcting photon loss of the oscillator. And in fact, this is the dominant error channel in our harmonic oscillator. So this is why we in particular are so interested in this GKP code. So to give you an idea of what this code is, so GKP stands for Gottesman, Kintaev, and Preskel, who founded the code in 2001. And I like to understand this quantum error correction code by thinking about its wave functions in the position and momentum space of the oscillator. And so in the infinite code, the plus Z eigenstate of the code is this superposition of infinitely squeezed states in position with the spacing here of 2 square root pi. And we can also plot that wave function in the momentum representation, and we see that it looks similar. It's also the superposition of squeezed momentum states with the spacing of square root pi. And we can also plot the orthogonal state in the code, the minus Z state, and we see that it looks very similar, except it's shifted over by half of a lattice spacing. And this means that the code states have disjoint support in position. So if you imagine there's a small shift error in either of the states, we can correct for those small shift errors and still have the logical information of the qubit. We can also plot the plus and minus superpositions on the block sphere, the plus x and minus x states here in the momentum representation. And we see that they look the exact same as the plus C and minus C code states in the position representation, where Q here is position. And this is why this we like to think of this qubit as a fully non-local bosonic qubit, because we have protection against both bit flip and phase flip type errors of this block sphere. And just by looking at these code states, you can see the various logical operators of this code. The first being that if you take any of these states and you shift it by 2 square root pi in position or momentum, you get back the same state. So the stabilizers of this code are displacements of 2 square root pi. In a similar way, the Pauli operators of the code are also displacements. If we take the plus z state, for example, and shift it by square root pi, we get the minus z state. So you see here that the x logical Pauli operator and the z Pauli operator, also the y Pauli operator, are displacements of the oscillator. In order to realize this code in an experiment, we have to realize a finite energy version of the code. And for this, we take those wave functions that I just introduced and we replace each of the infinitely squeezed peaks with a finitely squeezed Gaussian state. And we have an overall envelope which confines the total energy of the state. So this is what our actual wave functions look like in experiment for the plus e minus e state in position q momentum p, and the plus x minus x states in position q and momentum p wave functions. Okay, so this is, as you can see, sort of a very complicated wave function. So the question arises, how can we realize these states in an actual experiment? And so I can set the stage for the experiments that we use in order to realize these states. And so far, all of these experiments have used the same 2 building blocks, the first being a quantum harmonic oscillator where the GKP state lives, and the second being an auxiliary 2-level system qubit, which is used to control the state of the oscillator. So this is used to measure those error syndromes and to correct errors of the GKP state. We control this system using microwave drives, one on the oscillator epsilon of t and one on the qubit omega of t. And when you couple these 2 systems together, the oscillator inherits nonlinearity from the qubit. And this nonlinearity can be described by this Kerr coefficient K. And for GKP states, it's very important that this nonlinearity is very weak compared to other timescales in the problem. And this actually puts our system in a regime where the dispersive coupling between the oscillator and the qubit, chi, needs to be smaller than about 50 kilohertz, which is a very weak coupling compared to what is typically used in these experiments. So I'll show you in a slide or two how we sort of compensate for using such a weak coupling between the oscillator and the qubit. And we do these experiments in a 3D superconducting architecture where the oscillator is realized as a 3D aluminum post cavity. Typical T1s of these cavities are about 200 microseconds to 3 milliseconds, which is why we use these long-lived cavities. And we couple these to our auxiliary qubit, which is realized as the ground and excited states of a transmon, typically fabricated on a sapphire wafer. Okay, so we go back to this question of how can we realize these GKP states in experiment? Well, I would like to remind you that the stabilizers and the logicals for this code are displacement operators. And another way to say that is that if we have a GKP state that's been shifted by a small amount epsilon, then the state is still an eigenstate of the displacement operator. However, it has an eigenvalue, which is a phase, and that phase encodes a continuous error syndrome about this small displacement. So that's what makes this code a little bit different than your typical qubit codes, where you typically measure Pauli operators and you have plus or minus 1 outcomes, and you have discrete error syndromes. In this case, we actually have a continuous error syndrome given by the phase of the eigenvalue of this displacement operator. So we can change our question to, how can we measure a displacement, which is kind of a weird thing to ask since a displacement is a non-Hermitian operator. But in fact, we can read out bit by bit by bit the phase of a displacement operator by using a sort of typical phase estimation circuit. So what this means is that we take our auxiliary qubit and we put it in a plus superposition and we can apply a conditional displacement operation, which entangles the qubit in the oscillator. And at this point in the circuit, the expectation value of sigma x plus I sigma y of our auxiliary qubit encodes the expectation value of the displacement operator. So by measuring the qubit along different phases, we can extract bit by bit this small epsilon phase information about the shift of the GKP state. And this is sort of the building block that we use in all of these experiments in order to stabilize and prepare these GKP states. Okay, so now, we have this conditional displacement operation, and I would like to show you how we realize this operation in the experiment, especially considering the fact that we have this weak dispersive coupling between the oscillator and the transmon. So for this, we use a trick, which is a large displacement of the oscillator. So to understand this, you can think of the dispersive shift as a qubit state-dependent rotation of the oscillator. So if we displace the state of the oscillator in phase space, then we have this large lever arm that amplifies the effect of this dispersive interaction. And that's how we realize a fast entangling gate in the presence of a weak interaction strength. And so this gate is ultimately an echo sequence, which in the displaced frame of the dispersive Hamiltonian allows us to have a conditional displacement type interaction. This is coupling a quadrature of the oscillator to the sigma z value of the qubit, while echoing out these undesired rotations of the oscillator. And so to understand how this works, I have a little animation here of the gate acting on a squeeze state of the oscillator. And so what we do is we imagine that the qubit's in a superposition of E and G. We displace the oscillator out, and we see that we have this separation between the G and E states. We then displace the oscillator back to the center of phase space and apply a pi pulse to the qubit. This is our echo of the transmon. We then displace the oscillator to the other side of phase space, and this is a phase space echo of the oscillator. And we see that once we displace the state back to the center, overall, the action of this unitary is to perform a displacement of the oscillator conditioned on the state of the qubit, while echoing out all of these sort of undesired rotations. And this is how we realize this conditional displacement operation needed to do the phase estimation of the GKP stabilizers and logical operators. And the gate is described with this unitary, which is a displacement of the oscillator by beta over 2 if the qubit's in G, a displacement of the oscillator by minus beta over 2 if the qubit's in E, along with a flip of the qubit. And that's just that echo halfway through the gate. Okay, so this is all of the tools that we need to do this experiment. So I'd first like to describe what we did in 2020, which is the first experimental implementation of GKP. So I'm showing you a top-down view of our 3D aluminum superconducting package, which consists of a high Q oscillator. That's where the GKP state lives, in this case with the lifetime of 250 microseconds. That's coupled to a transmon with a chi of 28 kilohertz. And this chi is very weak. We do this in order to minimize the cavity curve, the cavity nonlinearity, which is about 100 times smaller than the chi is about 100 times smaller than the typical coupling used in these types of experiments. So how long does our qubit live using this phase estimation technique? Well, here is the lifetime results for the square GKP code, which is the code I introduced to you. And the way we do this experiment is that we initialize the plus X, plus Y, or plus C logical states of the code, and then we let that decay under its free evolution, and that's given by the X's here with the stabilization off. And then we compare that to the experiment where we turn on the stabilization shown here by the open circles. And you see that we have an improvement in the lifetime of the logical coherence relative to the uncorrected state. In this case, the X and Z lifetimes are 275 microseconds with the stabilization turned on, which is longer than the lifetime of the cavity. But the Y lifetime is 150 microseconds, which is shorter. And this asymmetry in the lifetimes comes from the fact that in the square code, there's actually an asymmetry between the logical operators of the X and Z and the Y. And so we can correct that by moving to a hexagonal GKP code where the X, Y, and Z logical operators are equivalent lengths in phase space of displacements. And we see that we indeed have corrected code where all three logical lifetimes are equal of 205 microseconds. However, this is still shorter than the lifetime of the cavity, so it's not yet beyond this break-even metric. Okay, since we're a bit short on time, I'm going to skip a few slides here and move to our recent 2023 experiment and discuss some of the improvements that we made in order to go beyond break-even. So first, we're using this new package with a slightly larger dispersive shift between the oscillator and transmon. And the first improvement we made was much better coherences across the board. So the oscillator is longer lived. And importantly, the transmon, which is the limiting factor in the first experiment, is now much longer lived with a lifetime approaching 300 microseconds using this new tantalum-based fabrication technology. We actually changed our quantum error correction protocol from something called the sharpen trim protocol, which I did not describe fully, but is just a variant of this phase estimation, to a new type of phase estimation called the small, big, small protocol, which I'll briefly mention in the next slide. And finally, another important aspect of this new experiment is that we're using online reinforcement learning in order to train all of the various parameters of this quantum error correction circuit. Okay, so in order to quantify the performance of quantum memory and compare these various experiments, we came up with this metric, which we call the quantum error correction coherence gain. And this metric is formed by looking at the channel fidelity to the identity channel of our error-corrected qubit and performing a short time expansion of that, that decay. And we compare this decay constant of the fidelity of the logical qubit to the best physical qubit in the system, which in our case is the oscillator. And we call this the QEC coherence gain. And so we can compare various quantum error correction memory experiments in this gain metric. And what this plot is showing you is every experiment has 2 points. The first is the best physical qubit, and then the arrow points to the best logical error-corrected qubit. And we see that in 2016, there was a first demonstration of a small error correction gain. And then 2020, this was our first GKP experiment where we realized the GKP code, but in fact, we realized a logical qubit with worse performance than the oscillator. And so our new 2023 work with GKP falls here, where we realize error-corrected qubit with a coherence gain of 2.3 relative to the best physical qubit in the system, which is the oscillator. And I'm going to quickly, since I'm running out of time here, go to the main results, which is the measurement of the logical lifetime. So in this experiment, we can measure the logical lifetime of the transmon and the oscillator shown here in the first two plots in order to find this logical fidelity to identity. And we can compare that here again to the logical performance of the GKP code. In a similar way, I'm showing in the open circles the uncorrected code, and the closed circles here is with the error correction turned on. And you can see that there's a substantial gain in the coherence of this qubit, achieving about a factor of 2.3 in this gain metric. So I'd like to just briefly mention what we're working on now, the next steps in GKP error correction. The first is that, as I mentioned, the limiting factor in these experiments is actually this ancilla transmon that we use to measure the stabilizers. So we're moving to exploring different types of ancilla controllers. And one that we're looking at in experiment now is actually another type of stabilized bosonic qubit called a KERCAT, which allows us to have an exponential suppression of bit flips of the ancilla qubit at the price of a linear increase in the phase flip rate. And it turns out that this is advantageous for the type of phase estimation circuits that we're running in these experiments. And finally, we have another experiment we're working on, which is realizing logical gates between these error-corrected qubits. In particular, we're using a three-wave mixer in order to perform the quadrature type coupling. This is coupling the position of one mode to the momentum of a second GKP mode. And this is the type of coupling that we need to realize the C0 gate between two stabilized GKP states. Okay, and with that, I'll say thank you and happy to take any questions if there's time.
Thank you very much, Alec, for the fantastic talk. And yeah, so we are really short on time, but if there is one question, I would be very happy to leave the floor to whomever would like to ask. Yeah, so Genois was fastest. Go ahead. Yeah.
Yes, very quick question. How important was this reinforcement learning part in the whole project? Like, was there a version that would work without all the reinforcement learning? Because that's very tricky to get right. Or was that?
Yeah, that's a good question. So we were not able to achieve beyond break even without the reinforcement learning. So the sort of human tuned version of the experiment could not go beyond break even. And in fact, when we implemented this reinforcement learning, we found that the optimal error correction circuits were actually slightly different than what the theory predicts. And this change in parameters is one of the things that led to the going beyond break even in the logical coherence. So it was very important.
One quick follow-up, Julia, if I can ask, but this is not.
I would encourage us. I'm so sorry, but we are really a little bit late. So I wouldn't, I'm sure. And I saw also that Alex has questions, probably because I saw camera. So I would encourage you, Alec, if you're available, I would encourage you both Genois and Axel to write your questions on the chat, either publicly or to Alec, so that in the meantime we can accommodate the start of Aziza talk. Thank you very much. I'm sorry that I cannot have time for questions. Thank you, Alec.
Thank you.
Okay, so now, Aziza, let's try to share your screen.
Yeah. Hi, everybody. I'm going to try from my iPad now. Let's see.
And sorry, Genois and Axel, for being very strict.
Okay, looks good. All right.
Okay.
And yes. All right.
Okay.
Okay. So sorry for the technical difficulties. Again, my name is Aziza. I'm a graduate student at MIT. I work in the Engineering Quantum Systems Lab, and specifically on the Waveguide Quantum Electrodynamics team. And we have been working on emitting and absorbing directional microwave photons for the past few years now, and I'd like to tell you all about this project. So the motivation behind this project is to establish quantum communication for robust computation. So we want to create quantum networks in order to enable modular and extensible quantum computation. And the way that this would work would be by distributing entanglement amongst computational nodes, such that the execution of the computation doesn't have to necessarily be local. And there are distributed computing schemes for large-scale quantum computation. But in terms of experimental realizations, there have been two schemes within superconducting qubits. So the first scheme, I'm simplifying it now, but I'm putting one qubit on one side of a resonator and a qubit on the other side. And I want qubit 1 and qubit 2 to communicate. And so typically this scheme involves using a resonant mode to transfer that state directly. And these schemes are bidirectional. They can be executed with high fidelities. However, you're limited in your node connectivity and distance. So if you want qubit 1 and qubit 2 to communicate, you do have to have a unique resonator in between them. And then if you want to link more nodes, you need more resonators. And then also the distance is constrained of the length between these two qubits. So as you make this resonator longer, the modes get closer together, and that complicates your communication protocol. So there's also another type of scheme, which instead of using a resonant mode in a resonator, you can use an itinerant photon in a unidirectional waveguide. And the way that this unidirectional waveguide is created is by terminating in 50 ohm at the other end. But in order to have that architecture, typically what's used is a circulator in the middle. And this is lossy and non-reciprocal and limits the fidelity of the communication protocol. Though this is a more tileable type of architecture, we are limited in loss because of those components such as circulators in the middle. So we're proposing a new type of modular quantum interconnect that takes the best of both of these two schemes. So our goal is to establish bidirectional communication with itinerant photons. So I'm showing you now in the abstract 2 modules an arbitrary distance away along a bidirectional waveguide. And we want these 2 modules to communicate via itinerant photons. And our platform is waveguide quantum electrodynamics. So a qubit on a waveguide, so we're superconducting qubits here, will decay its excitation in the form of spontaneous emission. And that's what we call a good quantum emitter. But the thing is, this wouldn't be a very good module because we can't control the direction of the photon once it's emitted. The qubit is equally likely to emit the photon into the leftward mode or the rightward mode. So half of the time, the photon goes to the left and half the time it goes to the right. So we can't control the propagation direction. And like I said, it's not a very good module. So instead, what we do is we put 2 of these qubits on a waveguide a specified distance apart, and we leverage a quantum interference effect between their simultaneous emission in order to create this module such that a photon propagates to the left or to the right on demand. So let me tell you a little bit more about this quantum interference effect. So like I've been telling you, we have 2 qubits and they're resonant. And I'm going to prepare them into this entangled state. They're both equally coupled at rate gamma to the same waveguide, and they're spaced a distance lambda over 4 apart, where lambda is the wavelength of the emission at frequency omega in the waveguide. So the qubit state is going to emit and become a photon state, but we have to figure out what that photon state is going to be. So we have to consider all the possibilities. So the first possibility is if qubit 1 emits a photon to the right. I'm denoting this by ket 0, 1. But there's also 2 phases that we have to keep track of in this analysis. So the first is the qubit state phase, and because qubit 1 was the emitter, if you look at the initial entangled state, the phase is 0. And then there's also the position phase. So we've referenced qubit 1 to x equals 0, so that phase is going to be 0. But now if we consider another possibility where qubit 2 emits a photon to the right, you'll see that the state phase is now e to the I pi over 2, because looking at the initial entangled state, the ket with the excited qubit 2 has a pi of e to the I pi over 2 phase in front of it. And then there's also the position phase, which is associated with this lambda over 4 distance apart. It's phased away pi over 2 in reference to the first qubit. So now we do the same analysis for the leftward photons, and you'll see that the phases cancel each other. And so the only possibility for the system is to emit a photon to the right. Now, there are a couple of technicalities we have to think about. So this system, 2 qubits lambda over 4 apart on a waveguide, will have a waveguide mediated coherent exchange coupling at rate gamma over 2. And this would disrupt our interference process because the qubits would be swapping population while they're emitting, and you can't faithfully transmit that entangled state onto the photon state. So what we do is we use a tunable coupler in between those two qubits to cancel that coupling and make sure that those two qubits are uncoupled and that our interference process will occur as we expect. So now, all that said, if I want to emit a photon to the left instead, what I have to do is just change the sign of the initial entangled state, and then the phase cancellations will flip, and we'll always have a photon that travels to the left, and the rightward possibilities will destructively interfere. So how do we do this in practice? Here's the device that we used to execute this experiment. In purple, that's the waveguide that I've been talking about, and the two qubits in orange are the emitter qubits. And the thing is, these are strongly coupled to the waveguide. So in practice, it's difficult to prepare them into this initial entangled state. So what we do instead is we introduce the pink qubits up top. These are the data qubits. And we couple all of the neighbors with tunable couplers. So the idea is if we can prepare the entangled state with the pink qubits and transfer it onto the orange qubits, then the orange qubits will decay and we'll have the interference process. So here's our directional photon emission protocol. This is how it goes. First, we introduce an excitation into the system just via a pi pulse on one of the data qubits in pink. Then we use parametric square root I swap gates to prepare that entangled state between the two pink data qubits. And we use a similar parametric exchange interaction to transfer the entangled state from the pink qubits to the orange qubits, which will then emit, and the interference effect will take place, resulting in a rightward propagating photon. So in more detail, this is the pulse sequence that we use. So there's the pi pulse, the square root I swap gate, and then the parametric exchange interactions, which are in the form of flux modulations. And so how do we actually detect this photon? At either end of the waveguide, we measure the voltage, which is proportional to the expectation of the A operator of the leftward mode and the rightward mode. And we could actually visualize this photon wave packet as a function of time. This is for a rightward photon, and this is for a leftward photon. And so we take that voltage signal, integrate it, and that's how we can figure out our moments and correlations of the system. And this is how we can characterize, is this a single photon? What's going on here, right? So we take those integrated voltage signals and we find all our moments and correlations. So here's the top is for a rightward propagating photon, and the bottom is for a leftward propagating photon. And these are the only non-zero or significant non-zero values are A dagger A for the leftward and rightward modes, meaning we have a single photon. We can map these moments and correlations using maximum likelihood estimation onto these density matrices. So here's the density matrix of the single photon states. And we've achieved 96% fidelity of leftward and rightward photons. So that was the end of the first part of the project, which is about emitting a photon. But what I really want to do is execute communication, right? That's the bigger goal behind this project. So this is the system that we're dealing with right now. And we have an emitter module on the left and an absorber module on the right. And the most basic communication scheme that we can execute with this type of system is emitting a photon and absorbing. And we want to simplify this as much as we possibly can, right? So absorption is going to be the time reverse of whatever you did to emit the photon. So to simplify that, we want to use a time symmetric photon wave packet. So we're using a secant hyperbolic shape here because it's time symmetric, and also the photon itself will exponentially decay, and secant hyperbolic has exponential decay functions involved. So it's the natural candidate for this type of request of our system. So in order to execute that time symmetric photon wave packet, we have to vary the coupling between the data qubits and the emitter qubits as a function of time. So when we release that photon, we can shape the pulse that releases it, and that will imprint itself on the shape of the photon. And so this is a simulation of an ideal symmetric photon emission. And here's the absorption, given that there are no other complications in the system. And so this is the theory, and here's how we actually executed it in the experiment. The same sequence is involved. We have the pi pulse on the data qubits, the entangling square root ISWAP gate. And the key difference is that now we're shaping the flux modulation on the couplers that transfer the excitation from the data qubits to the emitter qubits. And so this is what we see in the experiment. We've shaped the photon directionally as well. And we've achieved 97% fidelity or symmetry on the leftward photon and 95 on the rightward photon. And this was a very preliminary data. There's still a lot of optimization to do. But yes, so this is the first step in the absorption protocol. And also a key difference is that we've made the photon much faster by making it symmetric. So before our photons were upwards of 600 nanoseconds, and now they're around 200 nanoseconds. So faster communication means higher fidelities, and that's part of our goal. So now that we have symmetrized this photon, the photon absorption is the next step. And I'm still working on that in the experiment, so I can't show you the data yet, but here's a simulation of what we hope to show. This is the emitter and absorber module. In a simplified model, we have the emitter qubits and the data qubits, and the time-dependent coupling in between. The emitter module is going to emit a photon to the absorber module. And so what we hope to see is the population transfer. So the green is the data qubit population on the emitter module. So they start with half a population each because they're in the entangled state that will emit a photon to the right. And then during the emission and absorption process, all the emitter qubits get populated and depopulated at the same time. And then the pink line shows the data qubits on the absorber module population. So what we hope to show, what I'm showing you in this plot, is that the entangled state from the emitter qubits, the entangled state from the data qubits on the emitter module will be transferred to the data qubits on the absorber module. And so all of this is to say that we want to use this architecture to build a modular quantum network with high fidelity, high connectivity, and bidirectional communication. And the way that this would work would be by generating and absorbing photons that propagate in the direction that we choose. And this would serve as a tileable architecture for an all-to-all quantum network. And so I've talked a lot about the most simple communication protocol, but how do we extend this? So I'm showing you an array of modules that are not necessarily local in distance, and they're each coupled to their own quantum processing unit. And let's say all of them are tiled along the same one-dimensional waveguide. And let's say one QPU wants to send a photon to the other. Well, here's how you could do it. You have your emitter module. You can bypass as many modules in between just by detuning those emitter qubits, and then the absorber module. So you can emit and absorb a whole photon, but you can also use this scheme to prepare remote entanglement, and that will make way for gate teleportation schemes and distributed quantum computation at scale. I'd like to thank my team at MIT and MIT Lincoln Labs, without whom this work wouldn't have been possible. And I'd be happy to take any questions. Thank you.
Thank you very much, Aziza.
Yes.
Are there questions? There is a question from Simone. Yeah, Simone, go ahead.
Hello, thanks for a nice talk. It looks like, okay, you want to make this modular architecture, but have you thought also about error heralding or correction or mitigation strategies when you distribute information this way?
Yes, of course. So there's a lot of literature out there about purifying entanglement and what happens when you have a noisy channel. Those would also be next steps. So once you prepare that remote entanglement, of course, you can herald, you can do these things where you distill the entanglement as well. That would all function in this architecture. Yeah.
So you have not chosen a path yet to how to boost your fidelity, maybe at the expense of entanglement rate with using one of these techniques.
Right. Well, we're still working on it. Hopefully we don't have too much loss, because what we're imagining is all like, this is our quantum processor, right? And just like your classical processor has different chips that are responsible for different things, and they bus information along the processor itself. That's what we're imagining too. This isn't necessarily for something that's across different fridges or involves a lot of loss. And if everything's superconducting, hopefully we can mitigate that loss with on-chip techniques. Yeah. Like you're saying, I mean, we're pretty far away. I'm still absorbing the photon right now. So
Right. Okay,
maybe get
you.
back to me in a couple of years, or maybe the grad student that comes 5 years after me. I don't know.
All right. Thank you.
Yeah.
Excellent. Thank you very much, Aziza. Again, if there are more questions for Aziza, I would like to encourage you to write them in the chat, either publicly or personally. And then I would like to thank all the speakers of this first session. And I would like to invite everybody to take 7-minute breaks. So now we have time for a break, and a leg stretcher until 16. So we start in 7 minutes. See you then. And it's 16 o'clock, so we can, at least in Sweden, so we can resume the virtual WACQT workshop. So it's a pleasure to introduce Leon Koch, who is going to talk about the characterization and fabrication methods to reach high coherence superconducting quantum circuits. Please, Leon, the floor is yours.
Thanks a lot for the introduction. Yeah. I'm Leon, and I'm working together with Stefan Philipp in Munich. And today I'll talk to you about how to actually fabricate these quantum circuits that we use in our quantum computers, especially with regards to high coherence. Let's start with something that we probably all know, which is Fermi's golden rule, and which describes our decay rate of quantum states that are coupled to a noisy environment. And Fermi's golden rule tells us that with this forced factor, we can influence the coupling strength for our noisy environment. And in our circuits, we usually do this mainly by design. And with the second factor, which is the noise spectral density itself, this is something we can control in our fabrication. And since we want to minimize the decay rate, we also need to minimize the noise that we're coupling to. And this means that we need to especially remove all residues on the surface of our circuits. And it has been found out that especially the various interfaces, namely the metal substrate, the substrate air, and the metal air interface, are where most of the so-called two-level systems that are leading for our loss are residing. So we'll have a look at all these interfaces and try to get them as clean as possible in order to then in the end build very good qubits. In order to actually confirm that our fabrication optimization worked, we could always directly fabricate qubits, but since that is rather time consuming, as you will see later, we decided to use so-called coplanar waveguide resonators instead, which we use as sensors for our two-level systems. We probed the resonators that are coupled to a common feed line, and then from this Lorentzian dip, we can fit and extract the internal losses as it has been shown in the Sebastian Probst paper from 2015. And when we probe the resonators at different photon numbers or different input powers, we usually see a behavior like this. And we can see that the TLS losses, they strongly go down in with higher photon numbers. And from fitting to this curve, we can then extract our TLS losses and also our so-called delta zero losses, which are just the combination of different other losses that we're not too interested in at the moment, since our quantum computers are working rather in this TLS-dominated regime, at least usually. And for the people that rather like to talk about quality factors than losses, this is just the inverse of each other, of course. Let's shortly have a look on how we fabricate our coplanar waveguide resonators. And we usually start with an high-ohmic silicon 100 substrate. And in order to clean this metal substrate interface that I talked about before, which is usually the main loss channel in the beginning, we use 80-degree hot piranha solution, where we clean our wafers for 10 minutes inside it. This removes mainly organic contaminations on top of the wafers. Afterwards, we dip it for 30 seconds into an BOE solution. This contains HF and thereby removes the silicon oxide. So ideally, afterwards, we have a very nice silicon crystal, potentially with a hydrogen termination on top, on which we can now sputter 150 nanometer of niobium. Afterwards, we continue with optical lithography. So we spin coat an optical resist, expose it in a direct laser writer, and then we transfer the written design into the metal film by reactive ion etching using an SF6 chemistry in our lab. Afterwards, we of course remove the resist and potentially apply these post-process cleaning steps that I'll talk about later on. The resonators are designed with frequencies from 4 to 8 gigahertz, and the gap in our case is 6 micron, while the center conductor is 10 micron. This is how such a fully fabricated resonator chip looks like. So we have the common feed line and then 13 individual resonators coupled to it. And the first parameter that we looked at in our first run was the deposition temperature during the sputtering and how this now influences these internal losses that we want to minimize. We saw that the sputtering temperature has a rather small influence on the TLS losses. We do see some scaling, but the largest influence it actually had on the delta zero losses. So this could now either mean that, okay, we don't need to care about this parameter, or that it might become important later on. We anyhow moved on and looked into the X-ray diffraction measurements of the thin films that we fabricated, and there we looked especially at the full width half maximum of the rocking curves. All you need to know basically that this is a measure for the thin film crystallinity. Again, the TLS losses do not show a strong dependence on the crystallinity. However, the delta zero losses, they scale quite clearly with crystallinity. And this is now an indicator that we might use these measurements as a room temperature method to minimize losses, especially in the post-TLS regime. And with post-TLS regime, I mean a regime where we are not mainly limited by TLS losses anymore, but also by these delta zero losses that people usually don't care too much about yet. Now, of course, the question is, how do we get there? And this I'll try to convince you in the next slides that one can get there soon by using these post-lithography cleaning techniques. So when we measure one of these resonator chips with 13 resonators on top, without any further post-process cleaning, we usually end up around loss tangent or an internal losses of 0.19 ppm, so that's roughly a quality factor of 1,000,000. And then by cleaning these resonators very shortly in this BOE solution that I talked about, we can remove silicon oxides, and this roughly cuts the losses in half afterwards. The niobium oxides are etched roughly 600 times slower than the silicon oxides, so they are fairly unaffected by this technique. However, if we heavily increase the etching time, then we can also remove the niobium oxides, and this further reduces the losses to 0.33 ppm. And if we repeat this, or if we reoxidize this, then we can see that actually this is fairly stable and that the natively regrown oxides are less lossy than what we are calling the processing oxides. So after 3 days of air exposure, we only increase the losses by 0.03 ppm. So we still stay in the several millions of quality factor. We also repeated this in order to show that this technique was not just a lucky shot, or the sample was not just a lucky shot. And by 2 additional samples, we reached average internal losses of 0.24, so 4 million in quality factor. And the best resonator showed losses below 0.16 ppm, so that's a quality factor of over 6 millions. So now we're able to fabricate good resonators. However, we were looking at qubits, so we need to move on, use the same ground plane fabrication as we used for the resonators, but now also add so-called Josephson junctions, which we'll use as our our inductive but non-linear inductive element in our circuits. So for this, we spin coat a bilayer resist system consisting of Caesar and PMMA. We then, by e-beam lithography, define these Manhattan type openings for the junctions, and by a so-called double angle shadow evaporation under 45-degree angle, we first evaporate the bottom electrode, which is a 30 nanometer thick aluminum thin film. We then dynamically, or in a high pressure dynamic oxidation process, we build the tunnel barrier consisting of aluminum oxide before we rotate the sample and evaporate the top electrode, which is 70 nanometer thick. Afterwards, we need to lift off the excess metal and remove the resist. And then we have our junctions. In our fabrication, we also repeat this full e-beam cycle once more to fabricate the so-called bandages that you will see in a second. But this is basically a repetition of a very similar process. A finished chip then looks something like this. You have 4 individual qubits that are all addressable with their own resonator. And here in the inside, you can see the junctions in a microscope image. And these small rectangulars are the bandages that are connecting the niobium ground plane with the aluminum junctions. So everything here in gray is niobium, and the aluminum junctions you can barely see since they're only on the order of a few hundred of nanometer in size. We then measured the qubits and reached average T1 times of roughly 220 microseconds in our first samples and 300 microseconds in the best case, and similar T2 times of 162 microseconds or 250 microseconds in the best case. By now, currently in the fridge, we have a new generation of samples which show even higher T1 and T2 times. So the highest T1 time we've measured so far was 380 microseconds, and the highest T2 time was 470 microseconds. So this is quite at the state of the art and shows that niobium can, for example, perform similarly good as tantalum can, which is one of the more hyped materials at the moment. With this, I would like to shortly sum up. So I showed you that you can, by optimizing your sputtering parameters like the temperature, you can in general, or especially then by adding a post-process cleaning also, you can improve quality factors of resonators up to 6 millions, which will then also yield very good qubits with T1 times of well above 300 microseconds, and T2 times also around 470 microseconds in the maximum cases. In the future, we are looking also into alternative qubits. So we have first Flexonia now fabricated and the fridge, and they're being investigated at the moment. We're also scaling up our circuits. At the moment, the largest chip is a 6-qubit ring with tunable couplers in between that is also fully working. And in order to become more stable against reoxidation, we're looking into surface passivation techniques using so-called self-assembled monolayers. And in the longer run, we're also looking into newer materials. We have a new machine coming up for this soon, and of course 3D integration, since our long-term goal is also to scale up to a 100 qubit processor. With this, I would like to thank you for your attention, and thank also the team at the WMI, especially my closest collaborators and our professor Stefan Philipp, Nicholas Brokmoser, David Bunch, and Tamo Sievers are the people that are working in the fabrication together with me. Thank you very much.
Very nice. Thank you, Leon. Okay. I see that we have a question from Simone. Please, Simone, go ahead.
Thank you for a nice talk, and also for being very open about the details, or some details of your recipe at least. I think this is way to go in the field. And I have a little bit of a technical question about the relation between the internal quality factors in the coplanar waveguide resonators as opposed to the qubits. Now, I think at least a part of the Chalmers team has found out that typically we get better internal quality factors for the qubit than for the resonators on a purely aluminum-based process. But now for your niobium qubits, it seems that you get pretty much the same Q, or in your first generation, maybe even slightly worse Qs for the qubits. I was wondering if you could comment on that.
Yeah, certainly. So we saw that we have the two tuning knobs, which is on the one hand side the noise source itself, so our loss channels, our lossy surface oxides, and then the rest is basically how do you design your resonators versus your transmon qubits, and there it all comes down basically to the size. How much do you dilute the electric field? Our qubits are still rather small, so we could play the trick of making them a bit larger. That of course then plays a bit against scaling on the long term, and also at some point at least, and we're currently looking into this, when you apply this additional fabrication steps of the junctions, then this post-process cleaning probably, or you regrow some of these process oxides that you removed beforehand, and this can increase your losses again. So we believe that this is the cause of reaching not the very highest T1 times yet, but we're looking into techniques to improve this further, of course.
Okay, thank you. I think a few groups, including IMEC, for example, they started plotting these inverse Qs as a function of the participation ratio of the surfaces. And I think that's an interesting way to look at this.
That's definitely the right way to go. Yeah, I do agree.
Thank you very much.
Thank you.
Good. Are there other questions for Leon?
Yeah, maybe I have one.
Sure. Giovanna,
Hi, nice. Yeah, really nice talk. Thank you for sharing all this. And I have a question. So when you show this as a function of the this plot as a function of the temperature of your while we were doing the sputtering, have you then fabricated qubits for each of these cases? Have you fabricated chips in the qubit and look at the T1? Or
that would of course be a nice experiment, but this we haven't done.
Yeah, I understand. It's very time consuming to do. Yeah, it was a curiosity, but thank you.
Yeah.
Okay. More questions for Leon? We have 1 minute.
I have one question if there is time.
Yeah, please go ahead, Kazi.
Very nice talk, first of all. Nice results. One thing maybe I missed, like when you etch the niobium to make the pattern, do you even leave for the qubit fabrication process? Do you even leave out the area where you want to put the junctions? So is there any, how do you maintain the flatness of the silicon substrate when you do the etching, like the RIE of the niobium?
Okay.
Many of the process can actually etch the silicon, or does it not matter much?
Of course. So you have to highly work on your etching process in order to not end up with a very rough silicon substrate. I mean, in the beginning, we also had very rough silicon substrate, and very rough, I mean, RMS roughnesses of 3 to 10 nanometer, depending on the etching recipe. You can still put junctions on this, even if they're thin, but by now we optimized our etching recipe to go down to the, actually below our AFM limit. So it's only a couple hundred picometer in roughness.
Oh,
or at least
that's impressive
below that.
number.
And yeah, we can discuss this, but it of course is a bit detailed and probably too little time in 1 minute.
Yeah, I
you can
agree,
just
yeah.
send me a mail, and then I guess I can share this also.
I would love to hear that. Okay, thanks a lot.
You're welcome.
Okay, thank you very much again, Leon, for the great.
Problem.
Yeah, and I would like to invite then the next speaker, Kokail, to please try to share your screen.
Yes. Sorry. All right. Let me just shrink this. So can you see my screen?
We can see your screen. Yeah. Would you like to try to scroll down also?
Yeah.
Okay, good.
All right.
Great. Then I would like to introduce then Kokail, who is going to talk about unraveling the entanglement structure of correlated quantum matter. Please, Christian, the floor is yours.
Yeah. Hello, everybody. Thank you very much for the opportunity that I can give a talk here at WACQT. I'm a theorist working in Peter Zoller's group, and I'm going to report about the collaboration between theory and experiment, which was going on during the last 1.5 years. It's not published yet. It will be on the archive very soon. And the main thing I would like to convey here is that there is a new way, or an interesting way of looking at entanglement in quantum many-body systems. And we tried to see that in an experiment. I think it's interesting because it allows you to look at entanglement properties for pretty large subsystems. So before I go into the details, let me say a couple of words about quantum simulation in general, even though I know that most of you are familiar with the concept of quantum simulation. But usually we have some many-body system that we formulate in terms of a Hamiltonian. And as we heard in the first talk today from Kristel, the standard approach of computational physics would be to put this Hamiltonian on a classical computer and simply compute properties of this Hamiltonian, like ground state properties or dynamical properties. And but sometimes we know that this is too difficult, so we would rather like to design a special purpose quantum device that mimics the properties of this Hamiltonian in a controllable way. And this idea has been out there for many years now, and I just put here a couple of examples that I personally find very impressive. I'm mostly working in AMO physics, so you see a lot of examples from atom, molecular, and optical physics here. So we have, for instance, Rydberg atoms in optical tweezers, neutral atoms in optical lattices that can realize Hubbard models. Since recently, also molecules are trapped into optical tweezers. We have, of course, seen very impressive results with superconducting circuits that really push the boundaries of what is classically simulatable. And in Innsbruck, we are doing experiments with trapped ions, and these systems also developed very much due to the enormous efforts of our experimentalists. So when I started my PhD in 2018, we were doing experiments with 10 ions, and now these guys do experiments with more than 50 ions, and I will report on some of these experiments. One can ask the question, why is it actually necessary, or why is it not always possible to simulate such a system on a classical computer? And the actual reason is entanglement. It's the incapacity of classical computers to represent the entanglement of highly correlated quantum many-body states. And this is why these systems are interesting. It's because of entanglement. So let me elaborate a bit what we mean in many-body physics when we talk about entanglement. The situation that I have in mind is that we have some lattice model that is in a pure state psi. You can imagine this state as a low energy state of some local Hamiltonian. So this Hamiltonian is a sum of local operators acting kind of locally on the system. And if we are asking about entanglement, what we usually do is we separate the system into a region A and a region B. We take a bipartition and we look at the reduced density matrix of some subsystem. And the mixedness of this reduced density matrix tells us something about the entanglement between A and B. In particular, if this rho A would be a pure state, it means that there are no correlations between A and B. So what you can do now, and you can always do that, you can write this reduced density matrix basically in the form of a Gibbs state. You can write it as e to the minus h, where h is some Hermitian operator. This is always possible just because the reduced density matrix is a positive semi-definite matrix. And the topic of this talk is this operator here in the exponent, which we call the entanglement Hamiltonian. And if you don't understand anything in this talk, the main thing I try to convey is that in many interesting situations, in particular for low energy states of local Hamiltonians, this entanglement Hamiltonian has a very simple structure. Basically, it has the same structure as the system Hamiltonian. The operators are the same, but it's just that the coefficients are kind of different. So if your system Hamiltonian has XX terms, this entanglement Hamiltonian will also have XX terms. You can ask the question now, why is this interesting? An entanglement measure that we use to characterize entanglement is this von Neumann entropy. This is the expectation value of the logarithm of the density matrix. And if you have the reduced density matrix in this form, the logarithm of the density matrix is just this entanglement Hamiltonian itself. So the von Neumann entropy is simply the expectation value of this entanglement Hamiltonian. So if you know the entanglement Hamiltonian, you can really nicely study this von Neumann entropy for larger subsystem sizes. And another thing, if you have this entanglement Hamiltonian, you can look at its eigenspectrum, which we call the entanglement spectrum. And it turns out that you can use this entanglement spectrum to characterize topological phases of matter. If you have topological phases, this entanglement spectrum has a very, very peculiar structure. And what I'm going to tell you is the fact that this entanglement Hamiltonian is so simple allows us to learn it efficiently in experiments. And we have thus more efficient methods to characterize entanglement. So let me elaborate a little bit on that. We have now this entanglement Hamiltonian. Why has it this simple structure? Why should it be the case that the logarithm of the reduced density matrix is a simple thing? Let me talk a little bit about that. Maybe some of you encountered this before without realizing it. At least this is what happened to me. I encountered it the first time in the context of this eigenstate thermalization hypothesis. Let me briefly explain to you what this means. What this hypothesis says, if you have a local Hamiltonian and you diagonalize it, you look at the eigenspectrum, and you pick some state from the middle of the spectrum, then under certain conditions, this Hamiltonian has to be non-integrable and so on. But if these conditions are satisfied, what this eigenstate thermalization hypothesis tells you, if you take it seriously, is that the reduced density matrix takes the form of a Gibbs state. So I'm now focusing on, let's take now for the moment a one-dimensional system. We have here the subsystem A and the environment A bar. And the reduced density matrix has this form. And this is actually an example where this entanglement Hamiltonian has a very simple structure. It's just the Hamiltonian itself restricted to the subsystem. This HA is just a part of the system Hamiltonian. It turns out it's not quite true. There are some corrections to this form, some boundary corrections. So at the boundary, there are some deviations. But it turns out that you can account for these boundary corrections by not having a global temperature in front of this entanglement Hamiltonian, but rather a local inverse temperature. You have a beta I for each of your Hamiltonian components. And if you plot this beta I for your subsystem, this local temperature profile, it looks somehow like this. So it's constant in the bulk of the subsystem, and then usually at the boundary, it kind of drops off. Now, something that's interesting about this is that this temperature is basically independent of the size of the subsystem. So if you make the subsystem a little bit larger, it will look like this. And if you make it even larger, it will be like that, and so on. And this actually means that if you remember this formula for the von Neumann entropy, that it's basically the expectation value of the entanglement Hamiltonian. since the Hamiltonian is an extensive quantity, since the energy is extensive, it also means that your entropy will grow with the volume of the subsystem size. So in the 1D case, you will have a linear growth of the entropy. So this story, what I told you so far, this is basically known. People who work on the eigenstate thermalization hypothesis know this very well. And you can now ask the question, what happens if you go to the ground state? This thing is true for highly excited states of non-integrable Hamiltonians. But what happens if we go to low energy states? Has anybody ever investigated this? And it turns out that this has been done from people working in conformal field theory. So that's that's very peculiar. So people in conformal field theory, if you are sitting at a critical point, so if your state is invariant under conformal transformations, you can analytically derive how this temperature profile looks like. And it turns out it has the form of a parabola. And now this temperature profile depends on the size of the subsystem. If you make the subsystem a little bit larger, then these parabolas will get larger. And actually what this means is, if you recall that these curves that I'm plotting here are sort of local inverse temperatures, it's actually pretty intuitive that it looks like this for low energy states. It basically means that most of the entanglement the subsystem A has with its environment comes from the boundary. So the boundaries of your subsystem, they are very hot, and in the bulk, it's pretty cold. So this reflects the area law of entanglement. And if you would plot the von Neumann entropy in such a case, you would see that this entropy, because we are at a critical point, grows logarithmically with the subsystem size. So these are things that have been analytically derived for critical points. The question is, what happens if you go away from the critical point? Is this still true that this entanglement Hamiltonian is so simple? And the answer is yes. If you go away from the critical point, this has been investigated in this paper from Victor Eisler, then these parabolas, they change more to something that looks like triangles. And when the local temperature profile has this form, this logarithmic correction goes away and you get a true area law, which in the 1D case would just mean that the von Neumann entropy stays constant as a function of the subsystem size. So the stuff that I told you so far is, first of all, of academic interest, but it's also very useful for quantum simulation experiments and for measuring entanglement properties for the following reason. There has been a paper from Anurag Anshu et al. From Harvard, which show that if you have a Gibbs state, like a quantum state of this form, where you have like a local Hamiltonian in the exponent, this Hamiltonian can be learned efficiently from the quantum states, from local measurements. And efficiently means that the number of measurements that you need to learn this Hamiltonian, the structure of this Hamiltonian, up to a given error bar, scales cubically with the number of terms in your Hamiltonian. So there is a sample efficient way of learning this entanglement Hamiltonian. And this is what we did in a recent experiment together with Innsbruck. So up to now, together with the experimentalists in Innsbruck. So up to now, I just told you like a story, just showed you some curves that I drew by hand. So let's move into the lab and see how this thing look in practice. So what we do in this experiment is we study a Heisenberg model. So this is just a very simple nearest neighbor Heisenberg model in one dimension with an anisotropy. And what we can do with 51 ions now in this experiment, we can run variational quantum algorithms, in particular a variational quantum eigensolver. I'm not going into the details of that. This is really just, in the meanwhile, a standard tool for us that we use to prepare these states. And we optimize a VQE circuit such that we can prepare approximate ground states of this Heisenberg model. And once we have done that, after the circuit, for some subsystem, we can now perform measurements. So we draw some measurement data. And on these measurements, we can, from the measurements, we can learn the entanglement Hamiltonian. Because this is just a 15-minute talk, I don't really have time to explain how this works. This is written up in this in this paper, if you're interested. And in this way, we can analyze this entanglement Hamiltonian of the state that has been prepared. So before we do the experiment, let us look at some numerics. So what we did here was we did some simulations with matrix product states. What I show here is the von Neumann entropy as a function of subsystem size for states that we prepare with this VQE circuit. Looks actually pretty boring, this von Neumann entropy, so pretty much constant, which indicates that this is an area law in 1D. And we do this for two parameters of this Heisenberg Hamiltonian. Delta 1, the model should actually be critical, and the delta 1.7, we sort of move away from the critical point. And we can also compute all these lines at the moment are just classical matrix product state simulations. We can also compute this entanglement Hamiltonian, and it really turns out as predicted by conformal field theory. At the critical point, we see kind of parabolas for this entanglement Hamiltonian, and as we move them away from the critical point, they look more like triangles. So let's do the experiment and see what we get. When we do the experiment, these blue squares are now really experimental data where we average over many subsystems of this 51 ion chain. It kind of agrees with the theory simulations within the error bars, and we really see indications that we have a parabolic shape at this critical point, and if we move away, it becomes more like a triangular. And another thing we can do, we would like also to see now not only this for the ground states, but also for excited states. And what we do for this reason, we add a circuit that sort of heats up the state. So we heat up to some highly excited states of this Heisenberg model. And then we also see what's predicted from the eigenstate thermalization hypothesis. Now we see really that this entanglement entropy sort of grows linearly, more or less linearly with the subsystem size. And also in the entanglement Hamiltonian, we see this plateau instead of this parabolic deformation. So with this, I'm actually out of time. So let me conclude. I hope I was somehow able to convince you that this entanglement Hamiltonian is an interesting way of looking at entanglement features. We can use this to really scale things up. With this technique, we are now able to measure von Neumann entropies up to 20 qubits, which was really impossible before. I only showed results for one-dimensional systems. It also works in higher dimensions. We have a paper about that where we study this in a two-dimensional free fermion model. I analyzed only pure states in this talk. This thing can also extend it to mixed states. So for pure states, the reduced density matrix can be written as e to the minus this entanglement Hamiltonian, as I told you. If you want to characterize entanglement in mixed states, what you usually do is you look at this partial transposed density matrix. And this can also be written in a similar form where you don't have the entanglement Hamiltonian here, but something that's called negativity Hamiltonian. So in principle, this can be extended. And we also are working on quantum protocols to improve this procedure that sort of gets rid of any exponentially inefficient classical post-processing steps. So with this, I'm at the end and just would like to show you the team. So these are the guys on the theory side, which sort of came up with the protocol. And these are the people which do the experiments in the lab and which really did a great job in realizing this machine, pushing it up to 51 ions such that it works so well in the way it works now. Yeah, with this, I'm at the end. Thank you very much.
Thank you very much, Kristel, for the very nice talk. Let's see if there are questions for Kristel. While people warm up with their questions, I would like to ask you something.
Yes.
So you mentioned in the beginning that it's in principle very difficult to simulate these systems classically when we have a lot of entanglement, and then okay, you pick the example of the Heisenberg model. Actually, so I like to look into, for example, magic, and so then there is this, Gottesman theorem for which you can have a lot of entanglement. But if you don't have magic, you will be able to simulate your circuit or your states and your model. If you only have, for example, Clifford operations and stabilizer states. So I was wondering, where is the magic in the Heisenberg model? I don't know if there like in the phases of the model there are. Like, is it known that also must be an ingredient? I mean, entanglement is a necessary condition, but it's not sufficient for a model to be hard to sample or computationally intractable. Have you thought about that?
Right. So you say if the entanglement is magic, then it is easy to simulate. Is this?
No, if you only have entanglement.
Yeah.
But you don't have any magic. So, for example, if you start with, I mean, I come from quantum computing, so I have circuits in mind. So I think about states that are stabilizer states, for example, the eigenstates of the Pauli matrices. So here, eigenstates of S, Z, S, X, and S, Y.
Yeah.
And then I only have Clifford operations that can create a lot of entanglement, a lot of entangling gates. But then
but you can simulate it, or
yeah, exactly,
yeah. True. So you're asking why this is not possible for something like Hubbard models, for example?
Yeah, there must be some magic somewhere. I just was curious to know if it was very known that, for example, I don't know, the eigens.
I haven't thought about it in these terms. I don't think that it's really proven that these things are super hard to simulate, right? I think for something like the Hubbard model or for Heisenberg systems with frustration and things like this. So people in many body physics have just tried to do it for many years and failed. Yeah. So I haven't thought about it in terms of this magic, in terms of magic here.
Okay, now I was curious because of my background, but thank you so much for the talk.
Yeah, you're welcome.
If there are more questions for you, last chance to ask a question to Christian. Otherwise, I can. Okay, otherwise I can suggest that we thank Christian again, and that maybe Elie Genois could start to share the screen. So it is now my pleasure to introduce Elie Genois, who is going to talk about combining machine learning characterization and quantum optimal control to improve superconducting qubit operations. Go ahead, Elie, thank you.
All right, hello everyone. Thank you very much for being here, and thanks to the organizer. I'm really happy to be part of this really nice workshop. So today I have the chance of presenting the work I did in the group of Alexandre Blais here in Sherbrooke, Canada, in collaboration with Irfan Siddiqui's group at UC Berkeley. So in this talk, we're interested in designing the external quantum controls needed to implement rapid and high fidelity quantum operations. So we focus on quantum gates where some control hardware generates signals that travel down the fridge and create some dynamics on our qubits. And these dynamics, we want them to correspond to some given unitary, for example, a single qubit pi gate that is illustrated here. And one of the best approaches that we have to achieve this task is to use quantum optimal control theory, where we can use our physical modeling of the quantum system to design gate schemes that corresponds to the desired unitary. So for example, I illustrate here how we can modify the pole shape of our input signal based on the fidelity cost function for example, using a grape or a gradient ascent pulse engineering algorithm. And this works remarkably well in simulations. And using some clever optimization like this, we can find gates with many nines of fidelity. However, when implementing the same pulse on the actual quantum system, the optimal controls perform significantly worse than anticipated. So we might wonder, where are these missing nines of fidelity? And most of them can actually be attributed to some model bias, a mismatch between our model and the actual quantum dynamics of the system. And this model bias can be due to frequency and power dependent pulse distortion in the control lines, some coupling to spurious modes that are not included in the model, such as a cavity, couplers, two-level system, and so forth, and also crosstalk between the neighboring qubits and the control lines, etc. So as such, we understand that our physical model of the quantum system is not good enough to reach the desired level of precision on our gates. And in this work, we tackle this problem directly using some machine learning. And I will demonstrate the capabilities of our approach using both numerical and experimental data. So as we dive into the question of framing our optimal control task as a machine learning problem, we can directly think of feedback control, where we use our experimental observations to update the controls that we apply on our quantum system. So these observations can take the form of weak or predictive measurements on either the system of interest or some ancillary system. Then the model needs to make sense of these observations in order to steer the quantum system in the desired state. And recently, there have been many nice proposals of achieving this using model-free reinforcement learning, as we learned from Alec a bit earlier. However, the task of the machine learning model in this setting is quite difficult because first, it needs to learn a filter of what acquiring an observation means for the state of the quantum system. And it also needs to navigate the enormous control space in order to find pulse shapes that maximize our gate fidelity. So in this talk, I propose to break down this control problem into two parts that we do in succession. So first, we frame the quantum filtering as a supervised machine learning task, where the model learns to describe the quantum dynamics. And second, we use that trained model in a gradient-based optimal control to find a pulse shape that realize our target operation. So compared to a purely model-free feedback approach, this offers several advantages. First, by simplifying the learning task, it should improve its feasibility and also its scalability as we move towards controlling increasingly complex quantum systems. Second, this approach allows us to acquire detailed characterization information, which can be very valuable to understand and improve our quantum system. And finally, on the practical level, it's also very experimentally friendly, and we can learn an entire gate set at once, which can be quite useful. And this can be contrasted with the current reinforcement learning approach that only learn to perform a single operation. So let's explore in more details how that approach works. So first of all, to learn an accurate model of the quantum dynamics, we need to acquire some experimental data. So to do so, we drive our quantum system with a set of different pulses with some random and smooth pulse shapes of different durations. We then apply them on our quantum system and perform projective measurements to get bits of information about how the qubit state was transformed by these pulses. And we then average over these shots to create our training labels. Here's some expectation value of qubit observables. So using this data, we then perform a supervised machine learning training where the model learns a transformation from pulse shapes to qubit state, which should resemble a master equation capturing the open quantum system dynamics. So in this work for this blue box, we will use recurrent neural networks as they are a good architecture for modeling time order data with variable duration, which is exactly the type of data that our pulses take. And we also train on a physics-inspired loss function that includes a preparation and a positivity loss, in addition to the distance measure between the labels that we have and the predictions from the model, which we've shown in this previous work that can help a lot to learn accurate quantum dynamics. And second, once the model is trained, we use it directly in a gradient-based optimal control loop to find our control strategy. So at this point, the parameters of the model are fixed, and we really only optimize over the pulse shape. And this optimization can be done very fast on a GPU using state-of-the-art optimal control, we can also build a cost function that we want, such that the pulse shape that we find are easily implementable in the lab. And the whole idea is that now, since this model is trained on the actual experimental data, using the system in its desired configuration, and the hope is that the dynamics of the optimal pulse in the numerics and in the experiment will be much closer. So in the first part, let's see how that approach works on numerical data for the case of a driven transmon qubit, where we precisely know the quantum dynamics that are in play. And here we use a full transmon Hamiltonian with many levels. So first, we can look at a typical training of our recurrent neural network, trained on a few million different pulses. We use a long short-term memory cell, which is a type of recurrent neural network that is pretty common. So the axes on the plot show the mean squared error between the model prediction and our labels as a function of the training iteration, where an epoch means going through the entire data set once. So in the plot, we can see both the training and the validation loss come down to a minimum of about 5e-3, where the validation here serves as an evaluation of the model performance on a completely independent data set, which is a common practice in machine learning to avoid overfitting on our training data. And as shown by the dashed line, this value that we find, that we converge to, is pretty close to the lower bound, which is given by the sampling noise in our labels. Remembering that in the experiment, we can only acquire a finite number of projective shots. And as such, our labels are then only noisy estimators of the actual quantum state row that we're trying to predict. And with perfect predictions, we will reach this limit given by the dashed line. So if we look now at the quantum trajectories that such a trained neural network predicts, for example, here using a smooth Gaussian pulse as an input, and we can see this output on the right, where we obtain these nice Rabi oscillations for the X, Y, and Z qubit expectation values. So if we now compare with the true trajectory given by the master equation itself with the full lines, we can see really nice agreement. And we can also look at different pulse shapes, such as a random pulse in the middle and some sinusoidal drive on the bottom. And we see some really nice agreement once again. So for the sake of clarity, I want to emphasize that the neural network never has access to the full line given by the NE, only to the noisy qubit observables. As such, the quantum filtering task that we're trying to do here is a bit more involved than just a simple curve fitting on the right. So to get a more quantitative measure of the RNN performance, we can also compute the distance between the model predictions and the true quantum state, and do that for the entire test data set. And here we get a mean squared error about 2 orders of magnitude smaller than the validation loss, which means that the RNN is able to use our noisy labels in order to learn very accurate quantum dynamics. So this result validates the feasibility of realizing the quantum filtering task we're trying to do, which is the first step of our approach. But let's now explore how expensive it is to realize this task in practice. So here we address the question of how to best construct our pulse-shaped data set so that the machine learning model can learn an accurate quantum filter. So we consider that we can change both the number of different pulse shapes that we see and the number of projective shots that we repeat each of these pulses. And so first, the easy answer to increase the model accuracy is, of course, to just perform more experiments. So I show an example here of using 1 million different pulse shapes and just increasing the number of shots that we repeat these million pulses. So in the plot, we see how the neural network can do increasingly better at learning the filter as we give it better and better training labels. But of course, these additional experiments are costly to perform, and a much more realistic answer to the way of building the training data set is to consider only a finite number of experiments. For example, 1 million here, which might take a couple hours to realize in practice, and to consider how to balance between the number of different pulses we use and the number of shots that we repeat them. So interestingly, we find that there is this sweet spot at around a few tens of shots, where on the right, the behavior is that the neural network does not see enough diverse pulses to learn the filtering of arbitrary pulses. And on the left, the low number of shots make the label bad estimators of the true quantum state, and the neural network has trouble learning from them. And so we want to be in this sweet spot, but it turns out that not only the quantity of training data matters for learning, but also its quality. So as an aside result, I want to show here what happens when training our machine learning model on a data set made up only of random pulse shapes with no structure at all, with the idea that such a sampling will cover the enormous control space that we have optimally. However, that turns out to be a bad idea, and we can see that from looking at the performance of our RNN at predicting the dynamics. So when we inputted some random pulses, we see very nice agreement with the type of pulse shapes it was trained on. But it's actually very bad at predicting the dynamics produced by smooth pulses, as we can see from the large deviation between the predictions and the master equation, for example, when we just inputted a flat pulse. And since we want to use pulse shapes that are smooth experimentally, this behavior is very undesirable. And that's why in the results I've presented so far, we train on a combination of shapes drawn at random and of smooth pulses that are inspired by our analytical control schemes, such as flat, Gaussian, and sinusoidal pulses. Okay, so now that we've shown how to properly train our model and to do the filtering, the question is whether we can use that model to perform optimal control. And the answer is yes, as you might have guessed. So for example, I show here the optimal pulse shape for a pi gate around the x-axis performed on a 5-level transmon qubit. And we see the pulse shape here, which is smooth and respects all the realistic bandwidth limitations that we've included in the cost function. I also show on the right the quantum dynamics produced by this gate, both as predicted by the recurrent neural network with the dots and the true dynamics with the full lines. And interestingly, we can also use our trained model to find optimal pulses for arbitrary gates. So I show, for example, the average gate fidelity for some Clifford gates with 4 nines of fidelity, which is really nice. And I've also performed the same optimization on 300 random non-Clifford gates, just to show how we can consistently find good gates for arbitrary operations. So putting all these results together, it means that the machine learning model is able to find a very good heuristic of the actual quantum dynamics, which we can use to perform high-performing quantum gates. So with this proof of principle, we're now ready to move to the experiment. So our collaborator in Irfan's group have gracefully acquired some data on a transmon qubit for us, data on which we can train our neural network models. And I show here some example of what the model has learned from this data. So we see in this plot that by inputting some flat pulse, the neural network predicts some nice Rabi oscillations around the x and the y axes, as we would expect. But if we now double the drive amplitude of our flat pulse, we see that the neural network does not only learn Rabi oscillation with twice the frequency, but we actually see some detuned Rabi oscillations. So this means that the qubit gets shifted due to the higher drive power, which is indeed a behavior that is expected in the experiments. And we can play around with the input pulse that we input to our model to see some interesting features that we can use to debug our experiments. And taking a step back, this is an example of how the neural network can allow us to learn useful information about the quantum dynamics that are actually present in the device. And we are right now at the point of benchmarking our machine learning optimal control pulse shapes in the experiments with some preliminary tests showing promising results. So with that, I will conclude by saying that in this work, we've proposed a new approach to quantum control that mitigates the model bias. We've demonstrated the feasibility to learn a master equation from just microwave pulses and experimentally available observables, and demonstrated how this machine learning model can be used to successfully optimize for pulse shapes. So for our next step, I'm excited to test our optimal single qubit gates in the experiment and to compare their performance to standard pulses such as drag or grape. And we also plan on moving on to more complex quantum operations, such as parallel single qubit gates, 2-qubit gates, and applying the method we've developed to other quantum systems like the fluxonium or bosonic qubits. And with that, I will thank you very much for listening.
Thank you very much, Elie, for the very nice talk. Does anyone have questions for Elie? You can either raise your hand or unmute directly. Okay, Giovanna.
Yeah,
go
yes,
ahead.
I have a question.
Yeah.
I know that you say that, thanks, first of all, for the talk. It was, really informative and nice to see a mix between, theory and experiment. And I have a question so you have now started to try it on the Berkeley chip, right? Do you have an estimate of how long would it take for you to actually do this optimal control and improve? If you say you start with, I don't know, 99% fidelity, how long do you think your optimization routine is going to take to optimize the gate?
Yeah, that's a very good question. So the idea at first was not to do it online. So we just acquired a big data set of pulse, and then I just trained it and then proposed some pulses. But I think maybe the prospect will be something you can run maybe overnight. That will take a few hours because you really need to test a lot of different pulse shapes. So that can take on the order of hours just to take the data set. But the training of the model and the optimization loop are themselves pretty fast. You can do them in a few minutes. Yeah. So so I don't know yet about the precise online estimates, but that's a good. Thank you for the question.
Yeah, I'm looking forward to see the results. Yeah.
Okay, so it's now 17. I would like then to thank Elie again and all the speakers of this session with a big applause. And before everybody turns off, I'll switch because now we're going to have 1 hour break. But before the break, I would be very grateful if anyone could please turn your camera on for the group picture, like in every workshop. Let me first stop the recording.